exam 2 material will only be chapter 12, chemical kinetics. The reason we take kinetics first, and the reason that the authors of the textbook put chapter 12 first before chapter 13, which is equilibrium. Historically speaking, study of equilibrium came first. It was fleshed out, so to speak, before kinetics could get its feet on the ground. But in reality, the equilibrium is dependent upon kinetics. So as far as understanding concepts go, kinetics should come first, and that's what we're going to do. What do we mean by kinetics? Well, if you've had anybody, I've asked you this before, anybody had physics in you? No, you had physics, okay. So lots of times when you first start studying physics, they'll start you off on a study of statics. That is, nothing's moving, they're just opposing forces. Kinetics then comes after that. Kinetics is motion. If something is moving, it is said to be kinetic. So with respect to chemical reactions, see, good, I didn't skip one. Chemical reactions, we're talking about rates, how fast things happen. And there is some theory that helps us understand kinetics, but the study of kinetics is largely empirical. We make these measurements in the lab. How fast does a reaction proceed? One of the ways to express that is just, we say the rate of the reaction in terms of what? In terms of the concentration of some component. Right? Say we have an equation where we have A plus B yields C plus D. We can study the rate of that reaction based upon the appearance or disappearance of any one of those components. We usually work from the reactants because we generally start, in order to study reaction rates, we generally start with only reactants, and then we let the reaction run. So we'll take one of these, either A or B, or sometimes both. But for simplicity's sake, we're going to focus on just this one. So the reaction rate would be, what's the concentration after a certain time period? Concentration of A after a certain time period. And then subtract what was it when you started. Right, so final minus initial. That's typically how we do deltas. So that's a change in the concentration of A. And then how long did it take to get there? Well, the finishing time, the end time, minus the beginning time. Of course, if you start at time 0, that's going to be 0, and whatever time you measure will be the change in time. So that's one way to measure the rate of reaction. Rates of reactions are always measured in terms of some expression of concentration. Now, for practical purposes, we'll use, not in this upcoming lab, but in the future, we may use absolute values just to help the calculations. But the study itself is based upon concentrations. The concentration changes over time. And if we put square brackets, we mean molarity, the big M. Yeah. Okay, here we go. All right. This is a set of data of a real reaction. And these components for this reaction, nitrogen dioxide yields nitrogen monoxide and oxygen. So it's a decomposition reaction. And we're measuring from time 0 through time 400 seconds. And at each 50-second interval, we measure the amounts of each one of these gases. They're all gases. And expressed in the terms of molarity. Now, we could just as easily measure the partial pressures, and that would be an expression of concentration also. But this data set is based upon molarity. Notice we start off with 0.01 molar nitrogen dioxide and no products. Then after the first 50 seconds, some of the nitrogen dioxide is missing, right? And we've produced some nitrogen monoxide and oxygen. Notice the concentrations here. If we start off with 0.0100 molar at time 0, right? And this is nitrogen dioxide. I should have separated those better. And then we have nitrogen monoxide and oxygen, and these are 0 and 0. Then when we get to 50 seconds, we've only got 0.0079 left. Based on the stoichiometry of that problem, for every 2 of these, there should be 2 of those, or it's 1-to-1. So what are we missing here? Right? 0.0079 from 0.091 is 0.21, correct? That's how much we're missing there. So for every one of these we're missing, it should show up over here. And that's what we measure. The ratio for the disappearance of nitrogen dioxide and oxygen is a 2-to-1 ratio. So for every 2 of these, we only get 1 of those. So half of this should be the concentration of, let's see, that would be, like rounding off, okay, 11 molar, 0.0011. So the stoichiometry is holding. And you'll see that as we go down, if you lose some from the next one, it's going to show up over here in equal amounts for that one added on, and half amounts of that one added on. So the concentrations will increase over here and decrease over here. Now, that's the stoichiometry. The rate could be different. And so if we look at this, that, and we look at the disappearance of nitrogen dioxide, what happens after another 50-second interval? Are we going to lose another 0.0021? No, 0.0065 is where we're at now, 0.0065. So we only lost 0.0014, right? 0.0014. So 0.0014 should be added to this one. Should be 3.5. Right? Is that what we get? Yeah, 3.5. And then we add half of that to this one. So that one should be 0.168. Okay. So the stoichiometry is still holding, but the rate is not linear. We changed by that much in 50-second interval, but in another 56-second interval, we didn't change as much. So the rate's slowing down. Okay, and that's typical. And we could do that for the whole list, but
so what you did was you minus the 65 from the 35 to get
right.
14.
How much can it change? We're looking for the delta, the change.
Okay.
And the change here is 0.0014 rather than 0.0021 like the first one. So the rate of change is slowing down because it's the same time interval, but a smaller change in concentration. Okay. All right, so we could do that the whole way down, but we don't have time. If we look at this graph, we see it, it's easier to spot the rate of change. The green line up here, the green line is representing the disappearance of NO2. So you notice that at a certain time point, we talked about this before. We know how to determine the rate of a straight line. That's easy. Rise over run, right? You just measure that, and divide the two, and you get a slope. But what do you do with a curved line? A curved line has what's called instantaneous rate. So it's the rate at a given point on the curve. So if our curve did like this, then that rate would only be valid for that point right there. If we measure the rate at a different point, it would be a different rate. Okay, so it has a changing rate. All right. And we see as the NO2 decreases, we get a mirror image for the appearance of NO. Right? It's just like we flipped it over on itself, and it's increasing at the same instantaneous rates. But the slope for the appearance of O2 gives us a shallower curve. Okay. All right. So that's what we call instantaneous rate. And this is a concept that, if I don't know if any of you are going to take calculus, but if you do, this is one of the foundational concepts, is instantaneous rate of the curve. So the every chemical reaction, and we're staying with 2NO2 yields 2NO plus O2. Every reaction, chemical reaction, can be expressed in terms of a rate law. And that just says that the rate, and I'm going to stick with the concentration of NO2. The rate is equal to the concentration of NO2 in this case to some power. And there's a constant associated with it. These two are experimentally determined, those values. We can't deduce those values from the balanced equation. So we have to go in the lab like we're going to do next week and figure it out. This is called the order. In this case, the order of this reactant. This is the order assigned to that reactant. If we had an equation that was built up, well, actually, in this case, we've only got one reactant, so that's as far as we can go. If we had more than one reactant, say if we had an A and a B, we could say for the hypothetical reaction, we'd have a rate constant, and then we'd have our A to its order times our B to its order. Right. So these would be the orders for each of these individual reactants. And then the overall order would simply be N plus M. Okay. So if this power happened to be 1, and this one happened to be 2, that would be first order, second order. Then the overall order for the reaction would be 3. Okay. All right, that's the rate law. This is known as the differential rate law. The differential rate law. It's based upon concentration and some constant in the order. There's no time unit in there except what's buried in that concentration. If we integrate that law, and now I'm talking calculus again. let's see. Okay, that just reiterates what I said. The order has to be determined experimentally. And we're going to learn how to do that. So we're getting there. That's the differential rate law. And it shows the rate of the reaction that depends upon concentration only. So this rate depends upon that variable. That's a constant and that's a constant for this reaction. So this rate is a function of that value. The integrated rate law takes that information. Once we know what this is and that is, then we can integrate it over a period of time and get a different rate equation that provides a relationship of concentration and time as a variable. Okay. All right. I'll say more about the integrated rate law in just a minute. But I wanted to get this point in. We have to recognize, and this is a concept in equilibrium, that the reaction can go forward. And that's the way we've been writing it up to now. But reactions can go in reverse too. In other words, we could write this A plus B yields C plus D. But once you start building up some C's and D's, they can get together and go backwards. Right? So you can have reverse reactions. It depends on the reaction as to how important the reverse is. But when we study reaction rates, if we allow the reaction to go to the point where we can get a reverse, then we muddy the water, so to speak, because we're getting this return reaction and each one has its own rate constant. This could happen at a various certain rate, and then the reverse can happen with its own rate. And that is difficult to parse out the two for developing the rate law, unless you conduct the reaction at the very beginning where you only have reactants and the amount of produced products is relatively insignificant. We use, that's called the method of initial rates. In other words, you want to study it at the very beginning before the reverse reaction has a chance to influence the outcome. Okay. Let's see. One of the things about that determining the overall rate law for a reaction is that we can often infer individual steps that are required to produce. This is an overall expression of a reaction. What may happen is you may get one A and a B producing some intermediate X. And then that X would react with maybe another A, and that produces a C plus D. So these are elementary steps that we're trying to get at eventually. This is an overall reaction. There are elementary steps, and we'll talk about those a little more before this discussion is over. But we have to determine the overall rate law experimentally. But once we get a handle on the elementary steps, those elementary steps, the equations for the elementary steps can infer a rate law. So their stoichiometry will give us a handle on the individual steps rate laws. And then very often you can reassemble those individual steps into the overall and see if it matches up with what you determined experimentally. Okay. I mean, I packed a lot of words into that sentence, but they're all true. It'll make more sense once we get there, I think. Okay, this is just another, we're hammering that point home. These orders have to be determined, the orders and the rate constants overall have to be determined experimentally. Okay, here's the initial method of initial rates. We always start at time zero with reactants only. And generally speaking, since you can only get a certain amount of information from various concentrations, say, if we have a concentration of A and a concentration of B, then we can get information from that reaction. But that doesn't get us to the overall rate law. Then what we need to do is vary the concentrations so we get another reaction rate expression. And depending on how many reactants we have, determines how many experiments we have to perform for an initial rate. This will make more sense when we work an actual problem. All right, so if we have an experiment where we have the A and the B, and I guess each one of these has its coefficient. Little d. And we write an overall rate law for this, and it would just be the rate of the reaction is equal to some rate constant times the concentration of A to its order times the B to its order. That would be our starting point. Okay, how do exponents in the rate law compare to coefficients? All right, we're really going to hammer this point home, right? You can't determine from the overall equation, you can't determine the orders. It's impossible. If they appear, say A is equal to 1, and we experimentally determine that N is equal to 1, that's pure coincidence. It's not something that you can infer from the balanced equation. The balanced equation is an expression of stoichiometry only. It doesn't say anything about the rate, how they're converted. It doesn't say anything about mechanisms, which is those elementary steps. Now, that note down at the bottom is a re-emphasis of the fact that elementary rate law steps can be deduced from their separate equations. All right. So before we actually try to work an equation and initial rates experiment, we're going to talk about some of the most common orders, values of the powers, and how you recognize them. All right, we're going to talk about 3 of them. There's the 0 order, 1st order, and 2nd order. Okay, so the 0 order, I'll put here. 1st order, I'm going to put here so we can compare them. And 2nd order. Now these orders are not the only ones that you can assign to an equation. But it's a starting point. They're always going to be whole numbers, 0, 1st, and 2nd order. We're going to discover that when we do our reaction rates and calculate the orders for our reactants, that one of them might be a whole number and the other one might be a fraction. That's entirely possible. But this is where we're going to start. 0 order. So if we say 0 order, that means the rate is equal to some constant times, let's see, they're using A to the 0 power. That's 0 order. So what does that mean? Anything to the 0 power is 1. So this rate is equal to the constant. It doesn't care what the concentration of A is at the beginning. It's going to be a rate independent of the concentration. That's zero order. Now, this is the differential rate law. The integrated rate law, which is derived from this one, is concentration of A. Now, this does give us a handle on concentration and its relationship to time. So what this means is the concentration of A at the start, that's the initial. And then this is the concentration at some time, T, after so many seconds, minutes, hours, days, months, years, whatever. And then there's your rate constant. It's the same constant as this one right here. This is very useful because recognize the format. That's a straight line. Y equals mx plus b. That will give you a straight line. If you plot, if you plot time on the x-axis, let me do this. If you plot time on the x-axis and the concentration of A on the y-axis, then you get a negative slope, which is equal to K. Okay. So that says to me, if you have an experiment with various concentrations of A, initial A, that gives you this A over time. So we would take that data set that we were looking at the beginning. After 50-second intervals, you have concentrations of NO2. If you plot that data, time versus the concentration of NO2, and you get a straight line, then we know the order of NO2 in that reaction is 0. Okay, what else do we get from this equation? Well, there's one other thing that we can do. Well, there's the plot. Okay. You can also get an expression of half-life. So the half-life, let's see. You have an idea of what half-life is? No? Okay. Yeah.
Of a drug, but
Yeah, right. It's the same concept, right? Half-life in a chemical reaction, half-life of the drug in your body, or the half-life of a radioactive element over time, right? They're all the same concept. In other words, how long does it take for you to end up with half of the initial concentration? That's the half-life. And the half-life for a zero order reaction is the initial concentration divided by 2K. Okay. So these are the takeaway, the important things to take away from that discussion. So what this tells you is the half-life does depend on the initial concentration. Okay. And it's inversely proportional. It's directly proportional to the initial concentration, inversely proportional to the value of K. So as K goes up, the half-life goes down. Okay. Now let's go to let's see. Derivation of the zero order half-life equation. All right, you don't have to know that. I just threw that in there for fun. Yeah, it gave me a thrill to build that slide. Okay, for this one, now the rate is going to be equal to some constant, and this is a different constant than that one, times the concentration of A to the first power. And so this cell tells you that the rate is dependent upon the concentration of A, the initial concentration of A. The integrated rate law then is based upon the natural log of these A values. So the natural log of A equals, is it minus K? Yeah. Minus K times time plus the natural log of 0. So that tells me that if you plot the natural log of the value of NO2 against time, and it gives you a straight line, then it's not 0 order, it's first order. So we would plot it like this, right? Time here, you have natural log of A, and that would give you also a straight line with the slope of a negative K. So we're starting to build a picture of how you differentiate with your data set, how you differentiate among 0, first, or second order. You take your raw data and you do a transform on the concentrations, right? Set it up in your spreadsheet and have a column. These are the raw data values for A. And over here, you tell it to take the natural log of this in this cell. So natural log here, natural log there. You have to do those. And you get another data set with time versus natural log, and you plot those, see what they look like. Then we got half-life. So the half-life, in this case, is on the next slide, I think. Well, there's the plot of a different reaction, N2O5 decomposition. Is 0.693 divided by K. So this tells me that if your reaction is first order for A, then the half-life does not depend on the concentration. It only depends on the inverse of K. It's inversely proportional to K. Doesn't matter what you start with in concentration.
Do you have to have the half-life before you can do the first order? Does that make sense?
Actually, these are all related. So sometimes, to solve a problem, you may be given information in terms of the half-life. You can use the half-life to determine whether it's 0, first, or second order. And that will lead you to working the problem in the rest of the equations. Or sometimes you're given values that fit into this approach first, then you can go to the half-life. It works both ways because they are all related.
Won't you know it's first slide or, because of the 0.693 automatically, because that, or does that number change?
No, that's constant.
So you would automatically know that.
If you, right, if you're given,
That
if you're told it's first order, and you're also told what the half-life is, you can calculate K. Just use that equation. Yeah. Yeah, that's a good idea for a test problem.
now don't get ideas.
Okay. And there's the derivation of the first order half-life. Okay, we're going to look at this one, this sample problem, and probably answer the questions that you just asked. A first order reaction is 35% complete at the end of 55 minutes. What's the value of K? So we know it's first order, so we're in this region. And when we say it's 35% complete at the end of 55 minutes, I like to set up a table. Okay? You have a time table here, and you have a concentration table over here, a column. So at time 0, you have a certain amount of A. I don't know, what is it? They don't tell us. But they do tell us it's 35% complete at the end of 55 minutes. So at the end of 55 minutes, What does 35% complete mean? That means we've lost 35% of A. Right. So if we started out with X here, we're going to end up with X times 0. Getting bunched up here. Oh, what do we have left? Actually, we have 65% left, don't we? 0.65 remains because we've used up 0.35 of it.
Well, then wouldn't, that be 30.35 of the top, like where the sub zero? Since
No,
we used,
Wouldn't it be 0? Would it be
no, because this is the starting amount. It's the whole amount. And this is what's left after 55 minutes.
okay.
If it's 35% complete, we have 65% left.
And we're, so 0 at 0, it would be 100, correct?
Yeah, that would be 100%. Or just multiply by 1. Okay, so we know that this equation, and here's how we're going to. This requires a little algebra. If we know this is the integrated rate law that applies to that situation. And since we don't know what X was, but we do know the ratio, right? This gives us a ratio of the final versus the initial. Right? So the final amount is that, the initial amount is this. And that ratio is equal to 0.65. Because this is what's left versus what we started with, and that's what remains, 0.65, 65%. Okay? So that's why we took that equation and we solved it for the ratio of A to A0. Let's see, how do we do the steps here? Well, this requires an understanding of logarithms. Right, so if we say, I guess I'm going to have to erase this to make room. We want to get A and A0 on the same side of the equation. So if we do that, we move this one over here, it becomes a negative, right? Log of A minus log of A 0 equals minus KT. Is everybody with me so far? I just subtracted this from both sides. Okay, now here's the logarithm thing. When you say the log of A minus the log of A0, that's the same thing as saying the log of A divided by A0. Okay, that's a logarithmic identity. That transformation is one of the rules of logarithms. And that's equal to minus KT. Okay, we want to solve this so that we get A over A0. We don't want the log of A over A0. We want A over A0. So what does this mean? Right? What do logarithms mean? Logarithm base E. Right? Natural logs are base E. Common logs are base 10. Right? Puzzle looks. Okay. So how do we reconcile this one? Well, what we do is we take the anti-log of that value. And the anti-log is the base to that power. So this value right here, if we say, let's do it this way. Say log of A equals B. That's another way to say that is A is the power of 10. 10 to the B equals A. That's the anti-log. You take the base to this power. This is the power of 10 that equals that value. Right, that's what logarithms mean. So in this case, this ratio here, A over A0, is equal to E to the minus KT. Okay, that's how we got rid of the log. Let's see. Hold on a second.
Can you go ahead and put the 55 in there so people know that information? Because it's 55 minutes.
Yeah. Yeah, then the next step is to substitute the value that we know. So A over A0 is equal to minus is equal to 0.65. That's equal to this value right. All right. So what else do we know? Well, we know the time. Right? We know time is 55 minutes. Right. So if we put 55 in here for the t, now we have an equation and one unknown. Right there. Okay. Now what do we do with it? Well, the best way to deal with this is to take the natural log of both sides. Just go backwards now. We went this direction, one way to get there. Now we're going to take the natural log of both sides. So this looks like, I'm going to try not to skip a step. Natural log of E to the minus K 55 equals natural log of 0.65. Okay. What is the natural log of E to the power? If it's base E, then it's equal to minus K times 55. Okay. That's equal to the natural log of 0.65. Okay, natural log of 0.65. Let's see what that is. It should be LN on your calculator. 0.65 and then hit LN. That's minus 0.4308. And that's equal to minus K times 55. Okay. So we can get rid of the minus sign, so it's minus on both sides. And now we can say K is equal to 0.4308 divided by 55. And I get 0.0078.
Wait, so how did you put that in your calculator? You push LN 0.65.
Well, in my calculator, I put in 0.65 and then hit LN. But in yours, it's probably LN and then put the number in. Did you get that?
When I do your LN at 0.65, I get negative 4.3.
Yeah. Did you say 0?
0.43?
Yeah.
Yeah, negative 0.4308.
Yeah.
Okay.
And then you divide that by, wait, no, you just leave it.
Well, they're both, these are both negatives, so we can ignore the negatives because once we divide a negative into a negative, we get a positive.
Yeah, okay.
And that's 7.8 times 10 to the minus 3. And that's your K value. Now we typically, this expression of K gives you units of measure. But the K values can be complicated. So we typically don't put the value in there. We just say K is that value. Okay. That's enough of that. Now let's go to second order. Let's see. It's part of the problem working. We'll erase that. that and let me put the half-life back in here. Okay. Second order. The differential rate law is going to be K times the value of A to the second power. And to get a straight line integrated rate law out of this one, the transformation is not natural log of A, it's the inverse of A. So we take the inverse of A and plot it against the positive KT plus the inverse of the initial A. Okay. So if you got a set of data from a lab experiment, that gives you time and measured concentration. You put them in your spreadsheet. First transformation you do is natural log. Second transformation is inverse. Take the inverse of your values of concentration. And then you plot each one and see which one's the straight line. This one should give you a straight line that looks like 1 over A against time will be that way. And the slope is equal to K. And this has a, okay, there's an example. This has a half-life that's 1 over K. T N equals 1 over K times the. So this one is also dependent upon the concentration of A. And K, both of them. Okay. I'll point one thing out here. Zero order, first order, second order. What's the proportionality? What effect does K have on each one of those? This is for zero. T1/2 is proportional to 1 over K. T1/2 is proportional to 1 over K. T1/2 is proportional to 1 over K. They're all proportional to 1 over K. In addition to other stuff. So we're saying as K gets bigger, T1/2 gets smaller. For any of them. All right, so, well, there's the derivation. We'll move to this solution. Okay, let's see. We have a reaction where A is going to products. A starts out at 5 molar. And the first two half-lives are 25 and 50 minutes. All right. So let's see. What should I erase? This one?
Yeah.
This one? Okay. I can squeeze it in here. Okay, so we've got A going to products. The initial concentration, and I'm going to set up a table. Time versus concentration. So the initial concentration is said to be 5 molar. That's at time 0. The first half-life is 25 minutes. So after 25 minutes, we have half of that. Right? The second half-life is 50 minutes. What that means is this is our new starting point. So the second half-life is 50 minutes on top of that, which would be a total of 75 minutes. Now, we may not need to know that, but it's there. And the second half means half of that is left. Okay. So we want to write the rate law. Let's see. What we have to do is decide whether this is zero, first, or second order. So let's look at the half-lives. Can I simplify this? Yeah, okay. This will shorten the process. The rate law can't be first order because half-lives are dependent on concentration. Notice this is a different half-life, 50 minutes versus 25 minutes. Right. And first order is independent of concentration. Right. It should be the same half-life for both of them. I mean, same half-life for both of them, if it's first order. So now we're faced with zero versus second order. We eliminated first order already. If the rate law were zero order, then T1 half would be, zero, yeah, T1 half would be A0 over K. Okay, so if we set it up as zero order, then T1 half, 25, the first one, should be equal to the initial concentration, 5, divided by 2K, right? And if that's the case, then what's K? K would be equal to, bring K over here and put the 25 over there. That would be 5 divided by 50, right? 0.1.
How'd you do that?
I put the K over here and put the 25 over there times 2, which is 50 divided into 5. Okay. I do this, I skip steps sometimes.
I got it.
Okay. Now, how about the second one? 50 minutes equals, we're starting at 2.5 divided by 2 times K, right? If I bring K over here and put 2 times 50 over here, that's 2.5 divided by 100. So in that case, 2.5 divided by 100 is 0.025, right? That can't be. K is a constant. As you get two different K values, then it's not zero order. Okay. If we do the same thing, well, by process of elimination, that means it should be second order. But since there are a whole host of different orders that are possible, we better check it to be sure. So if we do the same calculation for that equation, then it would be 25 for the first one is 1 over K times 5. Right? So bring K over here, 25 over there. 1, the inverse of 25 times 5 is 0.008. K then is 0.008. Now let's do it for 50. So 50 is the second one is equal to 1 over K times the initial concentration is 2.5, right? Is that correct? Yeah, it should be. Okay, bring the K over here, put the 50 over there. 50 times 2.5. And then take the inverse. 0.00.
How do you do the inverse?
On your calculator, it should be 1 over X. Or it could be X to the minus 1.
Okay.
Okay.
So you times the bottom first and then you do the inverse.
Right, I take the K over here Then I put the 25 over here times 5. 5 times 25 is 75, right? So 1 divided by 75. And if I take K over here and the 50 over there, 50 times 2.5 should be 75 also.
Trying to calculate.
Okay, sure. Yeah. Thank you, Hannah.
Oh no, my calculator should be good.
Are we good?
Yeah.
Okay. So this just confirms that what we have is a second order equation. All right, let's go back to the questions. Wants to know, write the rate law. So the rate law is going to be second order. That is, the rate is going to be K, which is 0.008 times the concentration of A, second power. That's the rate law. The differential rate law for this equation. We calculated K already. And calculate A at 525 minutes. Okay. At 525 minutes, if we start off at 0 time, then we can say the elapsed time here is 525 minutes, correct? Yep. And the K we know is 0.008 plus 1 over the initial concentration. If we're starting from this one, the initial is 5. Right? So 1 over A, let me erase this. One over A is equal to that expression. Right. I got 0.08 here already. 525 times 0.08 is 4.2. So this one right here is 4.2. And then we want to add 1 divided by 5 is 0.2, isn't it? 0.2. So that's equal to 4.4. So take the inverse of 4.4. Here it is. And A equals 0.227 molar.
Say 2.2.
I'm sorry?
You said 2.2.
No, 0.22. 0.227. Yeah, let's see if the slide confirms. All right. There's our calculation to differentiate between 0 and second order. That gives us our K. All right. And then here's the calculation after 525 minutes. I'll round it off to 0.23. Okay. Those are a lot of steps, but there's a logic to it. Okay, so there are all our answers.
So on here it says equals 8.0 times 10⁻3. So do we need to write it out like that, or can we just put 0.008?
You can do it that way.
So it doesn't matter which way, really?
Mm-mm.
Okay.
If we want to be sticky about it, this needs 2 significant figures. So add a 0 on the end. That's why 8.0 times 10 to the minus 3 is 0.0080. Right? These are not significant. That one is significant.
What is n minus 1 min minus 1 mean? On that.
Oh, that's the inverse molarity, inverse minutes. They're in the denominator. You would say another way to write that is like 8.0 times 10 to the minus 3 over molarity times minutes. That minus 1 just means the inverse of. Okay. So how can you tell the difference among zero, first, and second order from their graphs? Plot them. Right? If you plot your data, the raw data, and you get a curve, it's not zero order. If you plot the natural log of your concentrations against time, and it's not a straight line, it's not first order. If you then plot the inverse of your concentrations against time and it's a straight line, you got second order.
So they all need to be straight lines then.
One of them, they won't all be straight lines. Only one of them will be a straight line, and that's the one that tells you which it is. So if you plot raw concentration, natural log concentration, inverse concentration, each against time, separate graphs, and then you look at them and say, which one is the straight line? That tells you which one. Okay. So let me make some room here. Yeah, pretty small. WD-40 is starting to wear them. It's harder to erase. It's the WD-40 side. Okay. So if we have a rate law that's expressed in terms of two reactants. How do you plot that data? Because our initial investigation, zero, first, and second order, was only in terms of one reactant. Right? What if you have another reactant in there, right? Its concentration can vary too. So how do you deal with that? That's what we're going to deal with next week when we do our kinetics experiment. Here's what you do. You take one of them. Let's just make this one. Make this one. Concentration. Let's see. Concentration. We want it to be concentration does not change. So how do you make the concentration of that component not change? You make it really high. You make it large. Make this so large that it effectively stays constant through the reaction. In other words, you use a minuscule amount of it in the process. Okay, what does that do for our rate expression? In that case, this is effectively constant. And this is a constant. So these two together give us a pseudo rate constant. Like that. Times A to the n. Now we can plot A. Straight values, natural log, inverse, and find out what the order is for this component, this reactant. Okay. Then we do it again at a different concentration of B, only it's still at a concentration that is not varied, doesn't change. So they're both high concentrations, but they're different. And we plot the data again, and we confirm that our first assumption, our first deduction of order for A is correct. Okay. Now, we're going to have a more complete discussion of this problem when we talk about chemical kinetics. Prepare for the lab. Okay, so hopefully I'll be able to do that next week after the review. Okay, but I think it's in the method also. Let me see if it's there. So you can get a heads up on it. Okay, there's a procedure. And there's questions. Here's we calculate the pH concentration. Yes. So on page, they're not the numbers right now. The last page. We talk about what you do with your data set. To determine what is this value right here. So what you're going to get actually is this pseudo rate constant is going to change. One pseudo rate constant is for the full, what we call the full strength of B. And then you're going to get another one where, in our case, we take half the concentration of B, but it's still high. And A is going to stay the same. Right, so you get a rate here, a different rate. This is a full rate and this is a half rate. So you get two different rates there. And if you ratio these two together, this rate against that rate, then we get a ratio of this rate, we get a ratio of those K's. And what are those K's equal to? Well, those K's are equal to the true K times B to the M. And we substitute those in here. And then the ratio is solvable for M, because we will have concentrations for the full strength of B base and the half strength of B. So that's a rough outline, and more details are in the method and we'll discuss in class. But that's the way we get around the type of reaction that has two components to try to determine what the I hate when that happens. The order. Try to determine what the order is for each component. Our A component is going to be the blue color dye, food dye, and the B component is going to be bleach. And so that's a teaser. Okay, this this table comes straight out of your book, and it just summarizes everything that we've talked about for 0, first, and second order. It's just there, everything in one place. Okay, what are we doing with this one? Do I have time to talk about it? Because our lab starts at 11:30. Okay. If we start off with A0 at 5 molar, and we know that K is 1 times 10 to the minus 2, what we're trying to do here is calculate the concentration of A after 30 seconds have passed. So for the first order, for the 0 order, we know that we want to use the integrated rate law because it has concentration variables in it and time. And after 30 seconds, we just put in those values and we calculate the final concentration of A. If it's 0 order, then A will be 4.7 molar after 30 seconds. If it's first order, we'll drop down to 3.7 molar. If it's second order, then we get 2 molar left over. So what that is saying is that the reaction rate proceeds faster for first order than second order, and it proceeds faster for second order than first order. So as the order increases, the rate increases, and you have less reactant left over. That's the whole point of that one slide. Okay, method of initial rates. Okay, so say we have this equation, and the first thing you notice about that equation is that the charges don't balance. Okay, so what you have to recognize is the only things that are involved in this reaction are the reactants and products that actually make a difference. The rest are spectators. So the manganate ion will have a counter cation with it, like potassium maybe. And the hydrogens are from an acid of some kind, right? That's what H plus indicates. And so on. So these are the data that were produced from 4 separate reactions, for 4 separate experiments. Now, why 4? Because we have an A and a B and a C on the reactant side. And what you need is the minimum number of experiments that will allow you to hold 2 of these constant and let the other one change. Right? So that's a probability. In math class, that'd be probability. So if A is a value of, let's just make something up. Let's say A is 1, B is 2, and C is 2. And then this one is 2, and that one's 2, and that one's 2. So if we compare this experiment with that experiment, we're allowing only for A to vary. Now, if we go back to 1 for this one and make that one 1, and this one 2. Oh, excuse me. Let's make this one 2. And that one 1. Now, if we compare these 2, then B is the one that's varying. So we need a 4th one to account for C. So if that's 1, and this one's 2, and this one's 2, then compare these 2, and that says C varies between these 2 experiments. So the upshot of this is, if you have 3 reactants, which is equal to your N, it's N plus 1. The number of reactants is N plus 1 is the number of experiments you need to design to give you holding 2 of them constant, or holding the other constant and letting one of them vary. You need 3 plus 1 in this case. All right. And all of these reactants take place under initial conditions. In other words, these are the concentrations at the start. See those little zeros on the brackets. That's the concentration at start and the initial rate at the very beginning of the reaction. So we're doing this so that the reverse reaction doesn't interfere. Now, what do you do with the data? Oh, it's not worked out. Okay. I can't do that in 5 minutes. All right, now we're going to talk about the method of initial rates. Right? It's not complicated, but you have to be organized. And the experiment must be set up properly so that you can use the data to answer the questions. So here's our example. This example reaction. Let's see. I'm going to spread it out because I'm going to use the equation as a header to put the data underneath. So 2MnO4 minus and 2, 2, and 4 plus 5 C2H2O4 and then 6H plus, and that yields product. We don't care about the product because this is initial rates. We only care about the reactants. Okay. All right. So here's the data. What we've got here is 4 separate experiments. And we determine the initial rate of each experiment with those concentrations. So for the experiment 1, right, we have a concentration of 1 times 10 to the minus 3. For the manganate ion, we have 1 times 10 to the minus 3 for the oxalate ion, and we have 1 molar for acidity, protons, hydrogen ions. And the rate comes out for this initial rate for this concentration of each at 2 times 10 to the minus 4. Okay. Now we have three more experiments. Notice that this one stays the same for the rest of them. And for the oxalate, we also stay the same. For the first two. And then for the second two, we allow it to change. And then for the last one, these are the same, and this one is allowed to change too. Now the rates for each one, 8 times 10 to the minus 4. Okay. 1.6 times 10 to the minus 3. And 1.6 times 10 to the minus 3. Okay. Notice what we've got here. The difference between this one and this one is a change in the manganate. These two do not change. And then the difference between these two is that manganate stays the same, hydrogen ion stays the same, and we allow oxalate to change. And then for the last one, the manganate and the oxalate don't change, but the hydrogen ions change. Right? That's the way we set up our experiments so that we can ratio any two of these to observe the change in the third one. All right, so what we need is a rate law to go by. So the rate law here is going to be, let's see, I'm going to run out of room. The rate law looks like this. Rate equals K times the concentration of manganate to its order, concentration of oxalate to its order, and the concentration of hydrogen ions to its order. I use a P there rather than a 0 so that we don't mistake it for an actual order number. Okay, so in order to solve the problem, we're going to set up a ratio. What we want to do is ratio in such a way that we don't get fractions, we get whole numbers if possible. So we want to put this one on top and this one on the bottom, because with this one on the bottom, we get a ratio of 2 into 8 is 4. So we're going to ratio experiment 2 to experiment 1. And the rate there is 8 for this one, minus 4, and 2 for this one. Now this expression is equal to this one. And this value is going to be 2 times 10 to the minus 3 to the n value. This one is going to be the same K. That doesn't change. And this one's going to be 1 times 10 to the minus 3 to the same power. And then we get these, which are exactly the same. 1.0 times 10 to the minus 3 to the m, and 1.0 times 10 to the minus 3 to the m. And then we have the hydrogen ions to the p's. Oops. Let me put the numbers in there. There should be a 1 and a 1. Okay, so we've taken experiment 2, the data from experiment 2 in this one, experiment from data 1 in this one, and we ratio them. Right? So what we notice is that these are exactly the same. Right? Denominator, numerator, it cancels. denominator, numerator cancels. K is the same as K, cancels. So now we bring down this one, 8 divided by 2 is 4. And this one is that one divided by that one to the n power. Remember, if you have a to the n divided by b to the n, that's the same as a divided by b to the n power. Right? So 2 divided by 1 is 2 to the n power. That means n equals 2. So now we can change this to 2. Right? Okay, next. We're going to have a different ratio. Right? We're going to have K here. We're going to have values here. Right? For this one, actually, let me leave that there and pull this one out and this one out. Leave that one alone. For this one, we want the oxalate to change and the others not. So these two stay the same, these two stay the same, and that allows this one to change. So that means we need experiment 3 divided by experiment 2. And the rates for 3 would be 1.6 times 10 to the minus 3. And 2 would be 8 times 10 to the minus 4. And the values here between these two are both 2 times 10 to the minus 3 and 2 times 10 to the minus 3. This one is going to be 2 divided by 1. And that one's going to be 1 divided by 1. Okay? So these cancel. Those two cancel. These don't cancel. Right? But they do equal to 2 to the m power. And what is 8? Notice if we change this to minus 4, this number becomes 16. So 8 into 16 is 2. So m must be 1. Okay, now we got this one. M is equal to 1. Right? The last one, we want to let the hydrogen ions vary. So it's between this one and that one. So this is going to be 4 divided by 3. Okay, now we need rates. The rate for 4 is 1.6 times 10 to the minus 3. 1.6 times 10 to the minus 3 for that one also. K is going to be the same. The value for manganate is not going to change, 2 and 2. The value for oxalate is going to be 2 divided by 2. And then the value here is going to be 2 divided by 1. Right? 2 divided by 1. So these cancel, and we get here is equal to 1. And we have here 2 to the p power. P must be equal to 0. So this reaction is 0 order with respect to hydrogen ion concentration. All right. So if this is 0, what does that law actually look like? If that's 0 power, that value is actually 1. So what we have is the rate equals K times the concentration of manganate to the second power times the concentration of oxalate, 2 to the first power, and the hydrogen ion term drops out because it's equal to 1. Okay, that's how you do initial rates. Oops, I forgot to calculate K. Okay, let's calculate K. In order to calculate K, all you need is this expression, rate equals this. And we take any one of these, plug in the value for rate, plug in the associated value for this term, and solve for K. So in this case, if we take the first one, concentration is 2 times 10 to the minus 4 squared. And this one is, oops, sorry. Actually, I was using this one. That's okay, we can use this one right here. Should work for any one of them. All right, so that one will be 2. This one will be 1 times 10 to the minus 3 to the first power equals the rate of 8 times 10 to the minus 4. So we just need to solve for K. All right, we'll square this value, divide it into that one. Take that one, divide it into that quotient, and that's equal to K. All right, so let's, I'm gonna put 8 exponent 4, put it in my calculator. Then I'm gonna square this one. 2 exponent 4, change the sign, and square it. And then divide it into this value. And then divide by 1 exponent to the minus 3. So we get 2. Did something wrong. Hold on a second. 2 exponent 4, change the sign. Let's square that. Okay. And times 1 exponent 3. Okay. And then divide that into 8 exponent 4. 2, I put something in here wrong somehow or other. Because it's not coming out 2 times 10 to the 5th. Hold on. Oh. Not minus 4. It's minus 3. Then we solve it, and K equals 2 times 10 to the 5th. In the 5th, not minus 5th. There we go. So that would be our K value right here. All right. So that's the method of initial rates. I know it's a lot of work. It's not difficult. You just have to stay organized and look for the ratios that will allow only one to vary at a time. Before I erase that top one, let me see what's coming up. We might need it. Okay, this goes back to what I mentioned earlier, right in here. What's happening in there? Most chemical reactions occur in a series of elementary steps. 2, of course. If it's less than 2, then it's the same as the overall. So it's 2 or more steps. In the process, usually an intermediate product is formed, and that intermediate product then enters into a subsequent reaction, and it disappears. Right? Intermediates cannot appear in the final balanced equation. So in that respect, it's difficult to determine what the intermediate is because you don't see it coming out of the reaction. If you have the technology, you may be able to identify it in real time, but it's difficult. So much of this is speculation, propose multiple mechanisms and say which ones are impossible and then which ones are best satisfy the data. That's where we're headed. Okay, here's an example. All right, I won't need this one then. For this example, we have nitrogen dioxide, carbon monoxide react to form nitrogen monoxide and carbon dioxide. So notice in the first step, you have two nitrogen dioxides react. Nitrogen is blue, oxygen's red. So we have those two funny looking figures reacting to produce nitrogen trioxide plus nitrogen monoxide. So what you're seeing is this intermediate and one of the products, right? This is nitrogen monoxide. Then the intermediate reacts with carbon monoxide and regenerates a nitrogen dioxide plus the carbon dioxide that is also a product. So this is a product, that's a product. This intermediate is created and then used up. And we used two nitrogen dioxides in the first step, but now we've recreated one of them. So if you look at it that way, as step one and step two, step one has nitrogen dioxide plus another nitrogen dioxide yields nitrogen trioxide plus nitrogen monoxide. And then the second step, we take this one over here plus carbon monoxide, and we produce carbon dioxide, plus we regenerate the NO2. So the first rule of a mechanism is that the elementary steps must add together to the overall equation. So let's see if it does. Okay. Let's pull them all down first. NO2 plus NO2 plus NO3 plus CO yields NO3 plus NO plus NO2 plus CO2. Okay. Now, if we've got the same terms on both sides of the equation, they cancel. Right? So we've got an NO here, we've got an NO2 here, it cancels with that one. We've got an NO3 intermediate, it cancels with that one. And that leaves us with NO2 plus carbon monoxide yields in nitrogen monoxide plus carbon dioxide. Now, is that the overall equation? Yes. So this mechanism satisfies that first rule. All right, we'll come back to that in a minute. Notice what we have in this mechanism is there are two species, two reactants, this one and that one. This is known as a bimolecular reaction because there are two species that collide. And this is, on the elementary step, a second order reaction. Remember I said the overall reaction does not give us any information about the order of the overall reaction, of order of the overall reaction and its reactants. But the elementary steps do give us that information. If we have two species coming together, that's bimolecular, and it's a second order reaction. If we only have one species in the elementary step, and it becomes something else, doesn't matter what the products are, but if it's the only reactant, that's unimolecular, and it's a first order reaction. The termolecular is where you have three components coming together. A, B, and C yield products. This elementary step is extremely rare. if it occurs, and if we can justify using it in our elementary steps, then it's a third order reaction. But it's very rare for this reason. These species have to come together, first of all, with enough energy to drive the reaction at that elementary step. Second, more importantly, they have to come oriented correctly. All three of them must meet at the same time and properly oriented so that bonds break and new bonds are formed. And that is a very rare occurrence. So we only use termolecular steps, elementary steps, when there's no other option. All right. When we have these several steps, we'll have step 1, step 2, we have step 3. And we know that their relative speeds, rates of reaction for the intermediate steps are in this relationship. This one's very slow. This one's fast relative to each other, right? It may take hours to complete, but relative to each other, this one's very slow and this one's fast relative to that one, and this one is only slow. The one that determines the rate of the reaction is the bottleneck, this one. So the overall rate of the rate of the overall reaction is determined by that one. I haven't seen any where the reaction rates for 2 of the steps are exactly the same. There's always one that's the slowest. Okay, and we can use this slowest step. We can take that elementary step and derive the overall rate expression. An example would be best. There's the first rule. The sum of the elementary steps must add up to the overall balanced equation for the reaction. If it doesn't meet that requirement, then you throw it out. And the mechanism must agree with the experimentally determined rate law. So if we determine a certain rate law for the overall reaction, and then we derive a rate law from the elementary steps, with this being the rate determining step, and they agree, that's good evidence that we have a valid mechanism. All right, here's another example. Dinitrogen pentoxide breaks down into nitrogen dioxide and oxygen. And these are the 3 steps that are given. All right, we're going to base our calculation of the overall rate law on the slowest step. NO2 plus NO3 yields NO plus O2 plus NO2. All right. First of all, we have to add them together. Sometimes you have to manipulate them, right? And use acceptable procedures. In this case, step 1 needs to be multiplied by 2. Why? Because we need 2 dinitrogen pentoxides. That way we can cancel 2 NO3s from the first step and the other NO3s from the second and third step. We can also cancel the NO2s from either side of the second step and NOs from either side of the second and third step, respectively. Then if we add them together, we get the overall reaction. All right. Let's use this one. Let's use this proposed theoretical reaction and its elementary steps to derive the rate law, right? We know the overall rate law is the overall reaction is A plus 2B yields C. Okay? And the proposed steps are these. Step 1 is A plus B yields D. And that is identified as a fast equilibrium. That is, as fast as the D is produced, it goes back to A and B. It's very fast. Fast equilibrium. Now we haven't talked about equilibrium yet. That comes in the next chapter. But for argument's sake, there is a rate constant for that direction, and there's a rate constant for the reverse direction. Okay? And they're not necessarily the same. But the process is very fast, which means it comes to equilibrium very quickly, and now the balance, you can't tell that there's a change in A plus B or D on either side. Once you reach equilibrium, then the amounts of each one, the concentrations of each one are stable. Then the slow step is this one. D plus B yields C. And this one also has a rate constant. Okay? So for this balanced equation, we start with the slow step. Right? This is slow. It's the rate determining step. So we can use the coefficients here to write a rate law for this elementary step. So what would that be? Well, the rate equals first order in D, right? Coefficient 1. First order in B with K sub 2 as the rate constant. Okay? Now, what's wrong with this picture? Let's see, I think I've got that in the slide. Well, I skipped a step. Add these together, do they add up to that one? We got 1A, we got 2 B's, and we got a C, and the D's cancel. So we met the first condition, I just didn't explain it. All right, so now we can go to the next. All right, so this is our starting point. This is the rate determining step. But where's the problem? The problem is that our overall rate law cannot include D. It is an intermediate. We got to get rid of D. So here's how we do it. All right? D is not a reactant. So we go to the fast equilibrium, and we notice that if we write a rate law for this side of the equation going that direction, let's see, let's move this back over here. If we write a rate law for this one going that direction, the rate would be equal to K1 A B, right? And the rate for the reverse reaction going from D the other direction would be the rate equals K to the minus 1 D. Now, the important part is this is an equilibrium. And we'll learn in chapter 13 that equilibrium is based upon reaction rates. Once you've established that the rate of the forward reaction equals the rate of the reverse reaction, you have equilibrium. So we're going to say this rate is equal to that rate. That means this expression is equal to this expression. Okay? Now, we have a term here. We can solve that equation for D and insert it in here. And that gets rid of D. So we're going to take this equation and we're going to solve it for D. That equals K1 over K minus 1 times A times B. All right, did I do that right? Keep the D over here, move the K1 over here, and A and B. So now we're going to take this and substitute it in here like that. So now the rate equals K2, K1 over K minus 1, and A times B, and then times B again. Okay? What's this? That's a constant. So all these together equal a constant. This term is to the first power, and this one is to the second power. So now we have a rate law with only the reactants in it. Now, the fact that this 2 shows up down here is coincidental. We cannot claim that one was derived from the other. This was derived from the elementary steps only. It's purely coincidental. All right, there it is in black and white. All right, and okay, it's in agreement. All right. See if I can get this finished before I run out of time. All right, we have a theory that governs the reaction rates. And it's called the collision theory. And it has a model. This collision model, actually, this is derived from the kinetic molecular theory of gases, and then it's modified to accompany liquids and solids. But the collision model is based upon the kinetic molecular theory. First of all, molecules must collide. If they don't collide, they can't react. That's the first condition. And for each collision, there is an activation energy, a minimum amount of energy required for the reaction to proceed from reactants to products. That's usually determined by actually the kinetic energy of the molecules when they collide. We don't know yet if there's enough energy there. So the way you increase that amount of energy is increase the temperature. So the temperature is a controlling factor for the reaction to meet this activation energy. And then the last requirement we've mentioned before is orientation. If the molecules are not oriented properly, say they come together with enough energy, but they're not oriented. They have to be this way in order to react. If they're this way, they just bounce off. No reaction. All right. So this activation energy is the energy that must be overcome. And this is what it looks like in a diagram. This is reaction progress. And this one is potential energy. Of all of the components at any one time. So if we have reactants at this level here, this is all the reactants energy. And then you have a collision. They have to meet this minimum amount of energy right here at that top in order for the reaction to proceed. And at this point, we have a transition state, I think your book calls it. Transition state, where bonds are beginning to be broken and reformed, but not completely. Sometimes we call this the activated complex. And if it meets this energy amount and just a smidge more, then it can roll over the top and come down to products. This is the potential energy of the products. Okay? So the activation energy is between here and there. That's the activation energy. Now, what's the difference between here and here? Well, it's a change in energy. Or for our purposes, it's enthalpy. Right? And if delta H is negative in this case, the energy has decreased, then we have an exothermic reaction. All right. And I've already said that. Now, a mathematical understanding of this process was proposed by I think he's Swedish, Svante Arrhenius. And he came up with this equation, where a constant value then is equal to this proportionality constant. Oops. There we go. A, and then E, like the natural log E, to the minus activation energy power divided by RT. And you know what R is. R is the ideal gas constant. Only this R has to have energy values in it, joules. So that's why we use 8.3145 instead of 0.08206, which has liter atmospheres in it. This is the one we use in this case. Okay, A is a constant that accounts for frequency of collisions and steric effects. So it has to be empirically determined. But we have access to a modified version of Arrhenius's equation. That's much more useful. This is the linear form of the Arrhenius equation. Okay. If we perform an experiment at 2 or more different temperatures, then it will have different K values for each temperature. And if we plot that data versus the inverse of Kelvin temperature, right? So this is Y, this is slope M, this is X, and this is, and that is the Y-intercept. So Y equals mx plus b will give us, if we plot the temperature in this form against the K's in that form, then we get a line, a straight line. And this is what it looks like for this example. So on the x-axis, we have the reciprocal of temperature in Kelvin. And on the y-axis, we have the natural log of K. And the slope of the line is equal to minus E sub A divided by R. Since R is a constant, then if we have the slope of the line, we can calculate the activation energy for this reaction. All right. So let's see. I got a little bit of room over here. Chemists commonly use a rule of thumb that an increase of 10 degrees Celsius or K for every increase of 10 K in temperature, the rate of the reaction doubles. So what I wanted to find out with this slide, I created this slide myself. What must be the activation energy for this statement to be true? So I had to pick a temperature range. So I picked 25 to 35. That's reasonable. 25 is normal room temperature, and 35 would be a little higher. So that's where we're headed. So first thing I had to do was convert temperatures to Kelvin. So I'm going from 25 to 35, or 298 K to 308 K. Then I set up the expression, and we're going to use the original. It's easier to find the answer this way. Well, it's the way I chose. Let's put it that way. You could probably use this one too. So what we want is to ratio the Ks, because if the reaction rate doubles, the K will double. So that means if we're going from K1 to K2, then K2 is equal to twice K1. Then we ratio K2 to K1. That's this first major step. And that ratios the Arrhenius equations with their respective temperatures. Oops. Then we simplify it. Right? We find that E to this equation is E to this one. When we go from E to this power divided by E to this power, then we say it's E to the power minus the other power. And since this one's a minus, it becomes a plus. Then we factor out E sub A over R and leave the T's behind. Now, what I'm trying to solve for is E sub A. So I have to insert temperature values. That's on the next slide. So actually what I did was solve for E sub A first, and then I inserted the temperature values and the value for the ideal gas constant. And the end result is that for this rule of thumb to be active, to be valid, the activation energy for the reaction must be 52.9 kilojoules. So that means if the activation energy is different, if it's less or more, then you will not have an exact doubling of the reaction for every increase in 10 degrees. All right, let's talk about catalysts. I'm going to leave that up there. So what is a catalyst? Well, first of all, a catalyst does one thing. It causes the reaction to go faster, speeds up the reaction. Second of all, it participates in the reaction, but it is not consumed by the reaction. In other words, a catalyst comes in one side, goes out the other. Apparently unchanged in the overall reaction. But if we look at the mechanisms, the individual elementary steps, we find that the catalyst is intimately involved with the reaction. It participates. And what it does is it provides an alternate pathway from reactants to products. And that pathway occurs at a much faster rate. Now, for this diagram, what that means is this will be the activation energy uncatalyzed, right, with no catalyst. If we put a catalyst in there, we find that the activation energy decreases. So this would be the activation energy catalyzed. Okay, we just decrease the activation energy. What does that mean? That means for any given temperature with a catalyst, there are more collisions that produce products because now they don't have to meet such a high standard of activation energy to proceed to products. Right? And this reaction, the way it's drawn is an endothermic reaction. In other words, the reactants are down here and the products are up here. The concept is the same either way. This is an explanation of what I just described as there are more collisions producing products with a catalyzed reaction. So if we look at the number of collisions with a given energy, we find that as the energy increases to the right, we have most of, for a given temperature, most of the collisions reside in this part, right? And an uncatalyzed reaction means that most of them don't have enough energy, right? Remember, temperature is a measure of the average kinetic energy of all the molecules in the substance. Right? They don't all have the same kinetic energy. It's an average. So some of them will be higher energy, some will be lower, and a lot of them will be kind of in the middle. So this sliver over here shows how many of the collisions actually exceed the activation energy. If we decrease the activation energy and the temperature is the same, then now we have more collisions. The activation energy moves further to one side, and that encompasses more collisions that can produce products. All right. We characterize catalysts in terms of their phase. If the catalyst is in a different phase than the reactants, then it's called a heterogeneous catalyst. A good example of that is a catalytic converter in your automobile exhaust. It has, there's a picture on the next slide. I'll get to it in a minute. In fact, let's do it now. The catalyst is a solid, right? It's platinum and palladium, which are deposited on this ceramic matrix, this honeycomb that's through which the gases flow. And the catalyst is in a solid phase, the reactants are in the gas phase. So what happens is those gases, in order to react, must absorb to the surface in order to react. So here are what we believe to be the steps for a heterogeneous catalyst reaction. We get adsorption, not absorption, adsorption of the reactants to the surface, and they are activated by proximity to the catalyst. In fact, they will migrate on the surface of the catalyst until they find the right orientation and the right catalyst. And then it will produce the intermediate stage, the activated complex or the transition state. When it does that, then you get products formed and they're released. They desorb from the surface. All right. I don't have time to tell you that story, so let's move on. The other type is homogeneous catalysts. These are catalysts that are in the same phase as the reactants. A good example is nature's catalysts, enzymes. Enzymes are biological or biochemical catalysts, but they have several distinctive features that are unique to them versus inorganic catalysts. I think I showed you this one last semester. The Haber-Bosch process, right? This is a gas, and this is with hydrogen, produces ammonia gas. So we need 2 of these and 3 of those. That reaction occurs without a catalyst, but not very fast and not very efficiently. So what Fritz Haber did, well, he did 2 things. He needed higher energy and lots of more collisions. So he did 2 things. He increased the temperature in the reaction vessel, and he increased the pressure, which means there are more molecules in there with opportunities to react. The problem with this reaction is it's exothermic. So if we put the energy term over here, or the delta A's, let's be consistent. If we put the enthalpy on that side, then if you increase the temperature, you're going to drive the reaction backwards from an equilibrium standpoint. So what he did was he introduced a catalyst. Solid iron powder. And that caused the reaction to proceed much faster to the product side. So the third thing he did was he took advantage of the difference in boiling points of the reactants and the product. These reactants boil at a much lower temperature than ammonia does. So all he had to do was bleed off some of the contents of the reaction vessel, run them through a cooler, just cold enough to condense the ammonia. The ammonia would drop out as a liquid. And then he would feed the gases back into the reaction chamber. So he was actually extracting that amount from each one and driving the reaction to the right. Okay, so this homogeneous catalyst, I told you that whole story based on a myth. This is not a homogeneous catalyst. This is heterogeneous. Right? If there'd been anybody in the class, you would have an opportunity. Well, actually, you're zoomed in. Opportunity to correct me, right? You thought I was talking about a homogeneous catalyst. I wasn't. I was talking about a heterogeneous catalyst. Now, the homogeneous catalyst has to be in the same phase. So here's an example. We're going to decompose hydrogen peroxide, which normally happens very slowly to the 3% hydrogen peroxide in your cabinet, in your medicine cabinet. So after a certain amount of time, it's no good anymore because it's decomposed. But in this case, we're going to speed it up really fast.
Can try here. So that's the technique. Just dump it right in and see what happens.
Oh wow. Okay.
Okay, so
Whoa.
we're releasing
okay.
lots and lots of oxygen gas. Okay. So why don't you go ahead and do yours now? Yours is a little bit different container. It's got, just dump it in really quick.
Okay.
Perfect. Yours is like more. And you just generate tons and tons of oxygen. It's being trapped at the soap, okay? It's like a supersized version of what kind of happens when you pour it on your body.
Sure.
Where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything,
Well,
if you will.
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff. This is like more of
Okay. What happened here was potassium iodide in aqueous solution was added to a 30% hydrogen peroxide. Right? It works better with the higher concentration. And then some dishwashing soap and food coloring was added for the foamy colored effect. But what happened was the hydrogen peroxide decomposed at much faster rate because of that iodide. This is the proposed mechanism for that decomposition. Notice the slow step for these elementary steps, 1, 2, 3, and 4. The slow step is the first one, where iodide ion combines with hydrogen peroxide and produces this species and that species, this intermediate. And the other steps are fast relative to the first one. But the first one is exceedingly faster than the simple decomposition of hydrogen peroxide. I had a student one time who was expecting a child, and his partner got an ultrasound. So they knew the gender, and they wanted to do a gender reveal party. So they used this procedure with either blue or red food coloring to reveal the gender of the child. Unfortunately, they got it wrong, They went back for another ultrasound and found it was the other gender. So they had to go back and do it over again. All right. Other types, that was a liquid catalyst, liquid reactant phase. The upcoming phases are all gas. And the problem is the decomposition of ozone into oxygen. Now, at upper altitudes, very high up in the Earth's atmosphere, ultraviolet light converts molecular oxygen into ozone. And ozone is a very, very efficient attenuator for ultraviolet radiation. So once you've got that ozone in the upper layer, it protects the lower layers of the atmosphere from ultraviolet damage. But if you have nitric oxide coming from incomplete combustion, usually from fossil fuels, it migrates into the upper atmosphere and it serves as a catalyst for this reaction, these two elementary steps. The nitrous oxide combines with ozone and produces nitrogen dioxide and oxygen. And then the free radical oxygen combines with NO2 to produce NO and O2. So what the reaction that is overall reaction is this free radical oxygen combining with ozone to produce oxygen. This normally occurs at a slow enough rate so that the sun's radiation can keep the ozone concentration at an acceptable level. But what we're doing is we're speeding up the reaction using this catalyst, the nitric oxide. Okay. Another way that can happen is with Freon. The original Freon, or Freon 12, and we don't have time to talk about the naming conventions for Freons, but the Freon they're talking about here is dichloro-difluoromethane. Migrates into the upper atmosphere, and then under the influence of ultraviolet light from the sun, decomposes and produces this free radical chlorine. Remember, free radicals are any atoms, ions, or molecules that have unpaired electrons. In this example, chlorine. If we draw the Lewis dot structure for chlorine, we find it has that. There's that unpaired electron. And that's the one that does the damage. So this free radical chlorine combines with the ozone, and it comes in one end, it goes out the other. That's the sign of a catalyst. One of the signs. It also has to speed the reaction up. And also degrades ozone into oxygen. All right. So I had a thought. It escaped me. Oh, I think I go back. No, it's gone. Sorry. So that's the introduction to chapter 12.